Not live in the city for sure.
11 by 8 or whatever.
You got your lab done?
So that's so good.
Did it at work last night.
He's got a power team.
Pancake shit on the way here. Otherwise, because like what I'm gonna ask you today. So funny.
Tuesday?
No. What have I ever been? So, Barbie and EE3180.
Yeah. Let's see what we had last class. Learn. I think you learned. Okay. Please.
Some of it?
How to operate. Right? So, not believe to God, of course, but based off evidence. Based off evidence. That was the theorem, that is the main theorem of AI and machine learning and Bayesian theorem or Bayesian method is what we found last class. We're going to have a couple of more examples today before switching to something new. But what is that something new that we want to talk? It's called sequential experiments. Sometimes random experiment is sequential. You do something random and then do another random and go forth. That's called sequential experiment. It has lots of applications. Dependency between these sequential experiments is very useful and practical. Like imagine for your project, final project or whatever, you want to model a traffic light. Traffic light, but not a normal traffic light. You want to kind of adaptive traffic light. You want to model adaptive traffic light or coordinated traffic lights. That traffic lights coordinate to each other. Do what? Anybody can tell me why traffic lights need to collaborate with each other or help each other? Yes?
Making sure one set of cars is going and while the other's stopped so they don't collide.
No, I'm talking about multiple traffic lights in different intersections, for example. Yes?
So you can pull out of McDonald's.
So what?
You can pull out of McDonald's.
What do you mean by that?
Oh, you have your Culver stop. Stop.
Okay. If you, for example,
Control the flow of traffic so you can pull
yes, that's the point.
like
Yes. Don't waste time. You don't waste time. When somebody pass one traffic light, what about the other traffic light is also collaborate? They don't waste time. This is like for future. Future, so many cities already implemented based off that. I don't know, in USA, in Canada, I saw some cities, small cities, of course, because when it gets big, so complex. That can be a good project, you know. You have a city, multiple intersections, and you as a scientist for a engineer wants to design a traffic light that minimize wasting time for driving, or maximize utility, whatever. That's the sequential experiment, because stopping in one traffic light depends on the other one. They are depend on each other. Okay? So most of sequential experiments, they have multiple stages. You do one step one, then like imagine you want to combine two random experiments together, like flipping a coin at the same time rolling a die. Not same time, one after each other. You want to see what is the possibility if, for example, I get head and I get, for example, even numbers together. This kind of actually random experiment called sequential experiments. They're sequential after each other. Lots of more applications, like for example in a factory. Imagine you have a factory making some stuff, some food, for example, and for factories we have making stuff, and then we have testing. We have two stages. One is testing, and we have another one is to inspection at the end. And they are not related. I mean, they are related in a case that, for example, if one tools, for example, pass testing, it has more possibility to also pass, for example, inspection. These kind of random experiments that depend on each other called sequential experiments. We're going to talk about that today. Lots of experiments, lots of actual practical applications for these topics. Also, we want to talk about something new. We want to talk about how we can graphically visualize probability. Because probability is something weird and hard to understand. What about we visualize it? We can visualize something. We cannot learn it nicer because we can see all the aspects of that. That's something that we want to start, but we're going to finish this class because this is so important. How we can visualize random experiments or probability in general, especially conditional probability. Conditional probability, because it's just make a graph for that. We're going to start with the tree today, and we'll see how tree, like data structure, not tree that you see outside, but same way. You have branches, you have leaves, you have parents, you have children. That structure is going to probability as well. This is what we want to talk today. Lots of good stuff. We're going to learn lots of things. But before that, we're going to go with some examples from last class, because Bayesian networks and Bayesian formula and Bayesian thinking is so important. So we're going to go for, first example is this medical testing that remained from last class. So let's see how probability can help in medical. Interesting. How? Probabilistic. So many things. One of the applications is medical. So we have a disease. I don't know what kind of disease you like. About but corona can be a good one. So imagine there is a disease that affects 1 out of 100. So it means probability of disease is 1 over 100. It's a very rare disease. It's not corona for sure. That means you're getting that disease just 1 over 100. It's very low. It's not okay. But we also have, but there is some medical test. So imagine there is a test that is a good test and detect that disease 99% of the time. The probability of testing positive, even you have disease, probability of, let's call positive P. Probability of positive given disease is given 0.99. You have this too. It's called modeling. When you want to model something, you need to write it in a proper way that we learn in this class, just probabilistic probability axioms. Okay? So we know that. What else we know? We know that this disease sometimes has a false positive. Oh, that's not good. So false positive means probability of positive, but you don't have that disease. Okay? So you test that, and you got positive. It means you might have that disease. But 5%, this is 5, not 590, okay, 5%. So probability of positive, even you don't have disease, not D. How I wrote that, okay? So we have these two. What do we want to find? We want to find what is probability of having disease, probability of disease, and positive, okay? So we have probability of positive disease, but we want disease positive. Come to our idea, one of application of Bayesian formula was that we are changing, reversing conditional probability. Here is exactly reverse. This is stuff coming from data. Maybe you ask me how we found probability of being positive and have disease, or probability of false negative, false positive, whatever, false positive, for example. How we find that? Based off experiment. We do 100 people test. That's called measurements, based off measurements. Every time we have measurements, what comes in your mind? Likelihood. Likelihood. So this is likelihood. Likelihood is a probability that's related to measurements, observations. That's likelihood. So we have this likelihood, and we want to find, we want to update our belief about the disease. Okay, this is coming from Bayes formula, of course, probability of positive disease, probability of disease, probability of positive. Okay, what we have, what we don't. We have most of them. We have here. Probability of positive disease, we have it, but we don't have probability of positive. Probability of positive is for normalization, remember? It's for normalization. In maximization or optimization, we don't care about this because it doesn't have D. Doesn't have D. D is something that we want to find. Okay? Anyway, but here we want it because we are asking, they ask us what is the probability. They didn't ask us what is disease. Okay, they asked us that. So because need to be probability, need to be actually between 0 and 1. Normalized, it needs to be normalized. So, how we find probability of positive? Because probability of positive is related to disease or not, and you have disease or not. So it's a complete space. We can write actually total theorem. Remember, we can say, okay, probability of positive, if you have disease, probability of disease plus probability of positive and not disease, probability of not disease, you add them together, this is the total theorem. Total theorem saying that, because in this space, you just have disease or not disease. And this is the probability of positive. So you add them together to find probability of positive. Simple, no? Good, so we have everything here. We can just put the numbers inside. I already did that. I think it's going to be 0.0594. Yeah, it's hard to multiplication and addition is not very complex math. So we have this. So we have everything. Okay, again, a small calculation is going to be 0.16. Almost 0.17. Okay? So it means what? It means you have only 17%, you know? You tested positive, but you the chance of having disease and you get positive is just 17%. Chance of testing positive and you have disease is so low, isn't it? So this is what we found after some calculation. So don't worry if you get positive, okay? This is what we want to go. Okay. Any question about that? Yes?
Could you explain the formula used for PFP?
Yeah. From that, I took that from here. This is total theorem. So how we add that, we actually compute these two. This is P and D, probability of P and D, and this is probability of P and not D.
Oh, and then use chain rule.
And change, yes. Okay. Yes. Yes. Thank you. More question? Okay, let's go another example. Jumping to something new. This is also very, this is a solution of that. Another example is that you see a lot is a spam detection. I'm sure you got lots of spam. Email, for example, you get some email that you don't know this is the real person or is just, something that you don't want it. And most of the time, if you open the content of that email, there is some free stuff there. Hey, come get this free and that, you know. And we made this example based off these questions that imagine you receive an email, okay, and you want to see if that's a spam or not. So we want to study in this case. So, but normally we tested, we have some data, for example, we measured so many times, we realized probability of receiving a spam is just 30%. Not that bad. Okay, so that's something that's coming from data. The things that coming from data, we call it data-driven. Based of data, we measure this stuff. Like 100 times we test that, and 30 times it was a spam. This is how we also, some more information from data coming up. We tested the word free in the contents of that spam or email, and we realized for spams, 70% there is a free word over there somewhere in that email. Maybe title, maybe contents. That's word free. Mention free. And 10%, the free was there and non-spam. It wasn't a spam, but it was free. For example, I don't know, from a school, you got an email, okay, come free pizza in the office, something like that. It's not a spam, but we might detect that as a spam. If we get hundreds of emails with contents free, spam. So we need to study this, how we access or not. So we got that also from data. When we get from data, this is likelihood. I mentioned here likelihood. Likelihood is something that you get it from data. Observations from multiple trial, and you test it and see. That's it. What we want to find? We want to find actually probability of what we want to find. Probability of a spam free there. What is this? For finding that, we also need to anyway, let I clear this one. Okay. So we also need to find probability of having free, because we need it for this formula, probability of spam even free. This is what we want to find. What is the probability of a spam if free is there? This is what we want to find. So based off this formula, it can come from likelihood, probability of free, even a spam, and probability of spam, and probability of having free. Okay. For finding probability of free, we go total theorem, and the rest is given. For total theorem, you always need to consider this Venn diagram. This helps you a lot. Is the space completed? We are considering that we have a spam or not a spam. It's complete, you know. Fill it up. We don't have 3 cases. we have another case, free, maybe spam, not spam. Yeah, I think, let's consider it just two cases. So if it's a spam and not a spam, we call them not a spam, this is not. Sometimes we show not with this. This is also not, but sometimes this is. In this class, we try to use this notation for not. Okay, but what we want to find is probability of having free. This is probability of having free, because some part of that is in a spam, some part is not a spam, so we need to add them up, and that's total theorem. This class is kind of overview of all amazing things that you learn. Okay, so that's the total theorem. The rest is just putting numbers. And the result is actually is 0.28, and this is 0.21. 75%, that's high. You get free in your email, be careful, 75%, it might be spam. This is what you get from all of these examples. Okay. Any question? Okay, now we want to switch to something new. Sequential experiments. Yes?
Sorry, under the likelihood where we get any likelihood of it being spam, why isn't the sample space adding to 1? 0.7 plus 0.1 adds to 0.8.
Not a spam? Because a spam and not a spam are complete each other. So not a spam is 1 minus spam. You ask, yeah? That equation
Under the new likelihood, no?
under what?
Why isn't likelihood the 0.7 and the 0.1 adding to 1? Does it matter?
I didn't get that.
I think I misunderstand, never mind.
So, yes, you are saying why this is likelihood. And, oh, yeah, for that one, why that is likelihood. That's actually prior. Yeah, I made a mistake.
Yeah, okay.
Yes, that's prior. Yes. Because, however, that's kind of knowing from data as well. But this is something we know about data. In this example, we consider that something that we know. Yes, yes, yes. That's good. Good question. Get my mistakes, you know. I make mistakes. I want you to find it up. Yeah, that's actually prior. I already mentioned that, prior property, but I mentioned this likelihood. Anything coming from, data is likelihood. Anything coming from some, I don't know, somebody told you, that's prior. Sometimes prior coming from the system as well, like a robot moving, based on the model. Based on the model, you can estimate what is going to be in another minute or another second. That's also prior. It's not coming from data, but I was guessing probability of a spam coming from data, but yeah, maybe not. In this example, not, okay? Let's do the next part. So, this is a clean version of that. This is one of the examples of sequential experiment. Imagine you want to design a factory to make resistors. You want to make resistors. You bought maybe you make, I don't know. You bought 3 machines, for example, machine 1. We call them, I don't know why in this example, M. Anyway, we have 3 machines, B1, B2, and B3. These 3 machines making resistors for us. But they are not very good, you know. Sometimes they mess up, you know, and is acceptable or not? Okay, so they make these transistors for us. This is 1 transistor, and you know, and we put these transistors in a bin before sending them out for packaging or whatever. We put them inside this bin, all here, okay, before pick them. Okay, that's good. So we have 3 machines. These 3 machines, we have some information. First of all, we define a transistor acceptable if, so for example, you want to make one resistor, sorry, you want to make a resistor. So this resistor, if is in a band of minus and plus 50, it should be accepted, okay? So this means value is plus or minus 50 of actually something that designed or labeled. We call that nominal, like designed. In this case, we call that acceptable. Imagine we pick some of these resistors from this bin, and we want to check it out to see are they okay or not. If it's between this variance, we accept it. Other than that, this is garbage. This is not good enough. Okay, so this is what we know. Another thing that we know, when we bought these machines, they gave us some information. They told us, okay, this machine B1, probability of be acceptable is 80%. For B2 is 90%, for B3 is 60%. So B3 probably doesn't use good technology, whatever. The resistor that is making 40% that's bad. But the second one is good. So we know this information. Okay. Another thing that we know is that the number of resistors that they are making. Like in each hour, B1 makes 3,000, B2 4,000, and B3 3,000. So we can use those to see if we take one resistor from the bin, what is the probability to be belong to which machine? So we need that as well. Because we add them together, in each hour, we make 10,000 resistors. If we pick one, probability of belonging to machine 1 is 30%. Because this is 3,000 over 10,000, 30%. And probability of belonging to machine 2, same, 40%. 4,000 over 10,000, 40%. And B3, or machine 3, is 30%. So we know that too. Okay, everything almost ready. What we want? Okay, this is what we want. What is probability that a randomly shipped resistor is acceptable? So we want to find probability of acceptable. We take one, that is good. Okay, so this is also coming from total probability because this space that we have has just coming from three machines, B1, B2, and B3. Again, Venn diagram. Okay? So you always need to consider, if you want to use total theorem, you need to make the space complete. This is the important part. And this blue one is probability of acceptable. So it has three parts, so we need to add them together. So it's going to be probability of actually coming from acceptable, B1, C1, probability of acceptable coming from B2, probability of B2, plus probability of acceptable B3, and probability of B3. Okay, so we have everything. Yeah, we have all of this. We have B2, okay? The rest is just adding together and 0.78. Okay, so that's good probability. 78%. If you take one from the bin, it is good one. It's acceptable. Good job. In terms of engineers that you did the design for this and make those, even though the B3 sucks, but still the other can compensate that. Especially the second one. Second one, making loss of resistors, and probability of acceptance is also very high. That helps, you know. Add together and help to, if you pick a couple of them, they're going to be acceptable. Good. But why in this example, why, because we already knew about total theorem. I mentioned that because of talking about probabilities that are related to the next step. There is multiple steps in these questions. Making them with these machines, add them together, and pick them randomly. And we want to see if it's acceptable or not. So it has multiple steps. This kind of experiments called sequential have multiple steps. And the next step is related to the last step. Acceptance related to which machine makes that. That's why it's related. Like that example that I mentioned for traffic light being green in next traffic light, it depends first traffic light. Is that green too? If it's green, it's better to next one be green as well. And if it's red, first one, it's better to next one be red too. You can see that example next slide. Okay, that type of probability is called sequential. Okay, let's get started. What is this? Sequential experiment, I talked too much about it. A type of experiment that has multiple stage or multiple step. it doesn't happen all at the same time. It has different steps, step by step. But that's not very, important. The important part is that these steps depend on each other. Each step is called a stage, and that's an example. That's resistors example. Step 1 is which machine made the resistor, and step 2 is that is acceptable or not. So each step called also sub-experiment because it has multiple experiments. Sub-experiment. To show those events, we can consider them like a parenthesis. Like, for example, coming from B1 and acceptable, something like that. With parentheses, we can show steps. Okay, what else we have? Okay, as I mentioned, that's the important part. That's the important part. The important part is that each stage depends on previous state. I mentioned may, but it's sequential. They are actually depend on previous stage. Okay. In that example, we already explained that. If resistor comes from B1, the probability of accept is 80%. If coming from B2, 60%, and so forth. Okay. Is there any way to show this relationship between these things and this sequential experiment much nicer? Yes. Graphical way. What about we consider, okay, we say, okay, if we have three machines, B1, B2, B3, like a node, and we come from start, and we say, okay, probability of B1, we write that in this edge, and this is directed like a tree. It's directed from root to leaves. This is probability of B2. This is probability of B3. And here is acceptable or not acceptable. Also acceptable, not acceptable. And here is the tricky part. This is conditional probability. Probability of acceptable coming from B1. Probability of not acceptable coming from B1. And so forth. Like for example, this one, probability of accept coming from B3. And the output is actually probability of A and B1. That is equal to probability of A given B1 multiply probability of B1. This graph shows all possibilities that happening in that question. This is called tree representation of probability. How we show a probability using graph, or tree is kind of graph. But it has some problems. It's growing so fast, isn't it? if you add another stage, one stage, it's going to, explode. You're growing so fast based off adding more steps or stages. Okay. The reason of growing so fast is repeating some nodes, like this is repeating many times. And when we go another stage, that's going to repeat more, Yeah. The reason is because this is tree. Tree is a simple data structure coming from root to leaves. Later on, we can see we can make it nicer. Okay. Yeah, as I explained, this is the tree diagram. What is tree diagram? A graphical representation of sequential experiment. Okay? Instead of writing formula, we can draw the stages. And we can also show the paths and conditional probability. Let's do that for, okay, we already did that for that. I have the here as well. How we can read the tree? We can start from root. Okay, let I show the picture first. Okay, this is exactly the same one, but with numbers. Okay, so I ask you, what is this? What is this one? That's the leaves for which path? This path. We have multiple paths. Any idea what is that coming from? What that means? Look at the path. Path coming from V1 and not A. This probability of V1 and not A. That based of chain rule is going to get to that. Okay, so how we can read that? Start from root, move left or right, do stages, and find these leaves. And the leaves are actually probability of all of those stages and together. P, for example, B1 and not A. So this is coming from that. And branches can be probability, like the first one, or conditional probability, like second one. So it means each node depends on its parents. Okay, so that's obvious, but not this last. If I am at this point, what's the chance of going? So for example, here, in probability of, if I am in B3, what is the chance of going to not A? In any stage, you consider that stage as something given, and then you find probability of something that's not given, and something that is given. Okay. Let's do another example that makes that more, tangible. Any questions? Good. Okay, so that's the example that we were making for. Traffic light. Okay, traffic light is a good example actually. We can implement that later in some traffic or something. But here is very simple case. We are saying there is a kind of intersection. Okay, there is a little town that maybe or Hancock. Small is just one road. We can implement that. There is two intersections, intersection 1 and intersection 2. And there is two lights here, traffic lights. This is one traffic light. Imagine the traffic moving from this direction. There is another traffic light. And these two traffic lights are kind of coordinating each other. This kind of example, this kind of traffic light called coordinated traffic light. Because they are coordinating to each other. They are helping each other. Helping to what? To maximize utility. What is utility? To not waste your driver's time in this case. Okay, what we have, we know that, for example, this is, I don't know, 2 kilometers. We know the maximum speed in this road is, for example, 45 miles per hour. So we know this. So based on this information, we know how long it takes time that a car pass from one to the other. So this is just prior information. Are we going to use that? No. For this example, maybe later. But for here, we don't care about the kilometers and stuff. We just care about this given information. We say, okay, probability of being green or red is just 50-50. The light is green or red in this example. We don't have yellow here, okay? Make it simple. So we just have 2, green and red, so they are half-half. We know that. Another thing that is important is this one. That's bring coordination. The coordination coming from this formula, mentioning that second light is not independent than the first one. They are depend each other. So how dependency works? Second light match to first light with probability of 80%. 80%, if the first one is green, the next is green too. Okay, so you model this. But here we consider that as a given value. So probability of being green in a second, if the first one is green, is 80%. Probability of second light be red, if the first one is also red, is also 80%. It's very high probability that if you are passing, the next one also you passing. And if you are stopping in the first one, the next one is also red. So you don't need to stop 2 times. If this gets red, you can pass the second one as well. That's a good strategy to make it coordinated, to make it like collaborating. Sometimes we call this system collaborating systems. Like if we consider this traffic lights as an agent, imagine they are autonomous agents. And they are collaborating each other to help us. That's the future. Future is going to be like that. You're going to have multiple agents in a city. These agents are just systems that are autonomous. When we call it autonomous, it means they make decisions by themselves. They make decisions by themselves. What is their decision? How much they stay red, how much they stay green, how much they collaborate each other to find these probabilities. The second light match with with the first one, in which probability they match to each other. It's helped them to actually maximize utility. That's always what we want, maximizing utility. But defining what is utility is a problem. Always we need to consider that one. Anyway, in this example, utility is to not waste time. And it's already given, you don't need to design it. But in real scenario, you need to design that, you need to find that. Based off this information that you have about the city, you have a map of the city, you have kilometers, you have, lots of data, you measure, you go there and count the cars that passing. You need to go automatic. And you want to make this system smart. This can be a good paper, actually, designing a smart traffic light. I have another project, same as this, but is a smart lane marking. So that's why this came to my mind. That's a good project. I can get some students to work on that. You can be too, if you like. Next semester. We can define a project regarding to a smart traffic light. Okay, so we have that. What we want, what is the probability that you wait for at least one light? These kind of questions are tricky. And you're saying, okay, waiting at least one light means probability of red 1 or red 2, or both. One of them be red, because you wait for at least one light. Okay, but computing, let's give you a secret. Computing probability of, I'm talking, it's just secret. No, it's not. Probability of, computing probability of multiple events that all together is very hard. We need to change them to and, because we have more information about and we can break that down to conditional, and conditional probability is easier to understand what's going on. But in this, it's so hard to, okay, R1 or R2 or both, so much stuff depend on this. Let's break that down. How we break that down? First of all, we know of course, axioms. We can use axioms, say, okay, this is probability of not probability of R1 or R2. Good? So far, so good. Okay, what about we play with this a little bit more? 1 minus, we know that the Morgan law can help us. If we have A, for example, or B, all not is equal to A naught and B naught. That's a De Morgan law. Okay, De Morgan law can be proved using Venn diagram too, okay? It's not complicated, but I'm sure you know that, you don't need to. It's going to be P of negative or not R1 and not R2. Okay, any question about this De Morgan law? listening but sleeping too? Okay, good. More listening. That's okay. Okay, so that's good. Okay, instead of computing actually, or we are computing these. And what about not R1? Because R1 and red and R1 and green one also make a complete space. It means if it's not R1 is equal to green one. This is also very tricky in this example. So this is going to be 1 minus probability of first one green, second one green 2. Because if it's not green, is white, is red. Okay? You just have these two choices, not more. Again, complete each other. So this is the last one that we wanted. So computing this is easy. What is probability of first one green and second one green? Okay, chain rule, of course. Probability of first one green, probability of second one green. I know I wrote it the other side issue. Yeah, but anyway, let us change the color to don't mix with this. Okay, so we have everything here. We have this one, and we have also this one. Okay, and what is the probability of weighting? Is equal to 1 minus 0.4, 0.6. I know, it was lots of tricky stuff. But at the end, we got it. Any question? I click to wake you up. Okay? I click. If you have questions, let me know in this. It wasn't that bad, you know. This is something that you can learn. Always when you see or, try to use the Morgan law to change it to and. Okay, with negating your events. And in this case, negation was very simple because green and red are complete each other. If it's not red is green, and if it's not green is red. Something like that. Okay, so that's good. Oh, I also draw actually picture. Okay, wait a second. We have more stuff to share here. So this is also the diagram. Graph or tree regarding you need to learn how to draw this. This is going to help you to understand the problem. Okay, anyway. This is the question that I ask you. Okay, but first I need to do something to, wait a second. Okay, you think about it. Try to write it up before responding. I'm gonna make the clicker very soon. I want you all solve it, please. can see the result here. Oh, subtract. The answer is C, actually. That's correct. I will start fixing. That's okay, no problem. Okay, why? Why is that? Okay, probability of probability of away. Okay, so what we want to find, this example is actually a real example. In cellular phone systems, most of the time we have multiple paging. And they are independent of each other. So, okay, so we know that. Imagine if we call F the event that the phone receives and receive the paging signal. Okay, so we know. So what is P of S? P of F. P of F is equal to P of success in 1, or success in 2, or success in 3. So, and based on whatever I mentioned is minus not success 1 and not success 2 and not success, not success 3. And because they are independent in this case, probability of not, from here, we can say probability of not success is equal to 0.2. And because they are equal, is 1 minus 2, 0.2. You add them together, it's going to be 8, 0, 0. Be 0.992. This is the correct answer. Good? Okay. Last part. Yes. Limitation. We have some limitation for tree showing, probabilistic things. Using graph or graphical way or visualize that is so important. Visualizing is these days very important, especially AI can help you for visualize things. When you think something, you can ask AI, can you visualize that for me? It can make a picture based off that. It's going to help you guys sometime. Some complex things you want to figure it out. And this is also visualization, but it has some limitation. If you use tree, the method that we mentioned to have multiple stage as a level of tree, we have some limitation. The first limitation is actually exponential growth. It's growing very fast. Tree is growing so fast. It's exponential. That's something that is important. Like if you have a tree, if you add one extra event, you kind of multiplying all the leaves. Like for example, if you have 2 levels, is like this, for example, imagine it's all binary. So we have just 2 first and the second is 2, but second become, and when you add another one, again 2, multiply that. It's like exponentially growing. From 4 become 8. 2, 4, 8, 16. 4, for example, 10 events, you have 1,024 paths. Each of these paths is one actually probability. It's probability of A1, for example, A2, A3, A1 or A2, A3. If you have 10 of these, you have 1,024 paths. It's so mess. Lots of extra things. Somehow we don't need them. And there is lots of repetition too. The second problem is these repeating events. Which one is repeating? Let's find it for this example. Which one is repeating? This is repeating with the color. This is same as this. This is same as this. And this. Same. The same event. For example, this was not A3. A3, this is not A3. A3 repeated 4 times. What about we just use graph? Imagine we just have graph. In graph, you don't need to repeat things. You have A1 and A1 naught, for example, A2, A2 naught, A3, A3 naught, and connect them together and make a graph. That's a graph. Later on, we're going to see how graph can help us. This is graph, that's a tree. Tree is a kind of graph, but it has some problems. Also, tree doesn't have loop, but graph has loop sometimes. We have directed graph or undirected graph. We have cyclic graph or acyclic graph. Then they can have cycle or not. This graph is undirected and cyclic because it has cycle. This is cycle. Okay? We're going to talk about them later. Anyway, hard to modify, that's another one. And poor for large systems. For a system like thousands of sensors or robots, this is not working good. What is the solution? Using graph. Yes. Okay. Hope you learned good enough. Have a good day. You have assignment. Don't forget that. I got a TA for you guys. You have a TA.
Have you looked at the lab for this week? Last week? No, I was. And then track it with an oscilloscope, like standard. Like it was coming up soon, so. I don't know, man. These someplace. I did the code last night, and I was like, oh, sweet, I'm done.
Yeah, I know. Look at the going over the things in high school. So unfortunately, I just wait up on it.